What are the challenges of multiplexing photonic qubits in hardware? Imagine trying to manage dozens of tiny light particles all at once, each carrying a piece of quantum information. Multiplexing photonic qubits in hardware is like that, an exciting idea with some tricky hurdles. First, photon loss is a big problem. As photons travel through waveguides, beam splitters, and couplers, some get absorbed or scattered, which means fewer photons reach their destination. This loss makes it harder to keep the quantum information accurate. Next, generating identical single photons on demand is tough. Many photon sources emit photons randomly, with different timings or spectral properties, making it hard to produce a steady stream of perfect photons for multiplexing. Achieving high-quality, on-demand photon sources that can be integrated into hardware is a major engineering challenge. Then there is the issue of keeping the quantum states intact as the system scales up. As more channels are added, maintaining coherence becomes more difficult because tiny differences in optical paths or timing can cause the quantum information to decohere or become noisy. Precise control over all the optical components is needed, which gets more complicated with larger systems. Another challenge is implementing reliable quantum gates between photons. Photons naturally interact very weakly, so creating gates that work every time is tough. Often, probabilistic methods or extra photons are used, but these add overhead and reduce success rates. Developing hardware that supports deterministic photon interactions or better error correction is still an ongoing process. Real-time control and error correction are also essential. The hardware must quickly generate, route, measure, and fix errors in photons to prevent mistakes from spreading. This requires fast, smart controllers that can handle all these tasks simultaneously. Lastly, integrating these photonic systems with classical control electronics adds another layer of complexity. The hardware must communicate seamlessly with classical systems for control and data readout, which demands compatible designs and efficient conversion between quantum and classical signals. In summary, making multiplexed photonic qubits work in hardware involves overcoming photon loss, creating perfect single photons on demand, maintaining coherence at larger scales, enabling reliable photon gates, managing real-time control and error correction, and integrating with classical systems. Solving these challenges is key to building practical, scalable quantum computers that use light particles to process information.